start recording. And we're going to make sure that everybody over here can see. Cool. Make sure I'm in the right chat. Just gonna play masking. Okay, guys in the Discord, can you hear me? Cool. Took a long time for that. Okay. All right. Oh, come on. That's another reason why we're behind schedule. Okay, by the way, you may have noticed I created this shared class folder for us. This is, I'm going to post when we finish the class. This is basically so you can access my lecture notes before and after class every day. And also I won't do it for Unit 1 because it would just be a pain. But from now on, all of the solutions to everything that we do, all of the take-home self-study assignments, when the exams come around, those solutions, all these solutions I'll also post up here in that notebook as well. Okay. So you have access to all that stuff.
For the assignments?
For what?
For the assignments?
Yeah.
Okay. Kind of like a study guide?
Well, you can use it for the exam. So you'll have, when you're getting ready for the exam, you'll have the study guide, you'll have all the solutions to the
because they're take-home, right?
assignments, because I'll take them, yeah.
Oh, okay.
But right now it's empty, right?
What's that?
Right now there's nothing uploaded?
Right now there's nothing in it. I mean, there's about to be this lecture when we're done here. But aside from that, nothing's happened. Okay. All right. Good afternoon, everybody. Any questions, comments, concerns before we get started today? Cool. And again, man, I'm sorry to pick on you, but you got to keep that mask over your nose. All right. So today's lecture, we're going to wrap up Chapter 3, and I'm just going to kind of call this like a Boolean algebra wrap-up. Let me use pink, let me use black. We're going to sort of put our discussion of Boolean algebra away for the rest of the semester. Obviously, we're going to keep using Boolean algebra, but our discussion of the nuts and bolts of Boolean algebra was going to finish today with a few minor details, some loose ends that we got to tie up. So the first one is, I know we ran out of energy, literally ran out of energy at the end of last class, but we finished talking about exclusive OR, right? Yeah. Talk about what it was? Okay. So what we're going to talk about today, to start off with, first thing we want to talk about is called the equivalence operation. All right. In the equivalence operation, we're going to denote with these three lines. We're going to say x is equivalent to y. And it's going to be, we're going to derive it from this. We're going to take x or x or y, and we're going to complement it. Now there isn't, make a note here, there isn't a De Morgan's theorem for x or, so we kind of have to be creative ourselves. And we want to start with, did we talk about the sort of basic Boolean expression for XOR? Did we get to that, or did we skip over that for time purposes?
I think we did.
Okay. Well, just in case, remember that XOR is x or y, but not x and y, right? One or the other, but not both. So we can write it as a Boolean expression this way, x or y and x and y not. And we're going to take that whole expression and complement it. Now we'll complement it using, now we'll use our De Morgan's theorems. So we'll say that that's equal to x or y not, or x and y not, right? That's De Morgan's theorem. What happens to this expression? What does that become? Just x and y, right? Because it's x and y. Anything inverted twice is just itself. So we'll be left with, let's go and keep this, x or y not, or x and y. Now what does De Morgan's theorem tell us about x or y not? What is that equal to?
X not, y not.
Say it again?
X prime, y prime.
Yeah, it's equal to x naught and y naught. So we've kind of reached our punchline here. We can say that the equivalence operation, x is equivalent to y, is equal to x naught, y naught, or x and y. Now let's demonstrate that with a truth table. Let's say that we have x and y on one end, 0, 0, 0, 1, 1, 0, 1, 1. And let's go ahead and put this together from these sort of constituent components, because we haven't talked about, really spent so much time talking about building a truth table. So what is our column for x not going to be? Good, 1, 1, 0, 0. Remember the inverse, 1, 1 of whatever the x column is. Now how about y naught?
1, 0, 0.
Yeah, 1, 0, 1, 0. And finally, well, not finally, but finally for this step, x naught and y naught, that column is going to be what? It's going to be 1, 0, 0, 0, right? Now on the flip side, let's see, we got some more stuff. We've got x and y, which is just the regular AND operation. So what's its truth table column equal to? Say it again.
0, 0, 0, 1.
You're absolutely correct. Keyboard cooperate. 0, 0, 0, 1. And now we're finally ready to put our last piece together. So x naught, y naught, or x, y. That column is going to be equal to what?
1, 0, 0.
Yeah, 1, 0, 0, 1. So if we tie that all the way back to the beginning, we'll see that the equivalence operation is what we expected, right? It's 1 when x and y are both 0, and it's 1 when x and y are both 1. Sort of the definition of equivalence. We'll say this. We'll say that x equivalent to y is equal to 1 if and only if x is equal to y. So this operation does the pretty handy thing of looking at two bits, two signals, and telling us, are they the same thing or not? It's not hard to imagine that this is going to be pretty useful down the road, right? Okay. So a couple of other details. Let's see, we did that with the truth table. We can represent it with a logic diagram or a schematic symbol. So we'll say represent x is equivalent to y with a logic, call it logic symbol. All right. So what this looks like is this, it's just x and y, and our box. Inside the box, it's just the symbol, 3 lines. And the output is x is equivalent to y. Now here's the catch. This is not commonly used. In fact, I've never seen it used anywhere outside of this lesson. What is more commonly used is, if we go all the way back to the top, this business. The fact that the equivalence is the inverse of XOR. So we'll say instead, we use what we call X NOR to represent equivalence. So instead we use X NOR. The symbol for that is just going to look like this. Same deal, we got X, we got Y, we have an XOR gate. My terrible drawing, with a little dot on the end to indicate that it's inverted. Right? That dot means invert. And the result there is X equivalent to Y, which we've just shown is equal to X XOR Y. Not or X NOR. So the opposite of XOR. All right. Any questions about that? Edward, no, there is nothing from the previous lectures. We're just starting right here. All right. So that's equivalent to an XOR. So in addition to and, or, and not, we now have XOR, and we have XNOR. And we know that XNOR is useful because it tells us if our signals are equivalent or not. All right. Any other questions about that? All right, well, let's move along. Part 2 of today's lecture concerns the consensus theorem. Right? Because remember, we have 4 simplification theorems. And they are, first, the Uniting Theorem, which says that X and Y, or X and Y naught, is just equal to X. We have the Absorption Theorem, which says that X or X and Y is equal to X. Third, we have the Elimination Theorem, which says that X or X naught and Y is equal to X or Y. And then our fourth one, the one we're about to talk about, is the Consensus Theorem. It does some useful things and is worth taking a moment to discuss all on its own. The Consensus Theorem. So, as with the rest of these theorems, up here I only drew the sum of products form. And we're going to sort of pretend that product of sums doesn't exist a lot of the time. So all of these have a product of sums form, but we only wrote out the sum of products form. Well, let's go ahead and write out both of them for the consensus theorem. The sum of products form for the consensus theorem, remember, is X and Y, or X naught and Z, or Y and Z is equal to X and Y, or X naught and Z. And the product of sums form is just everything flipped over, right? X or Y and X naught or Z and Y or Z is equal to X or Y and X naught or Z. Now, in both of these cases, the thing that gets eliminated, the Y and Z and the Y or Z, are both referred to as the consensus term. And consensus terms are redundant and can be removed. Make a note of this. Or not the, but consensus terms are redundant and may be removed from the expression. All right. And as a side note, they can also be added. And we'll see why that can be useful as well. All right. Questions about the basic structure of the consensus theorem. X and Y, or X naught and Z, or Y and Z is equal to X and Y, or X naught and Z. All right. So let's do an example. And in this example, let's look for this. So I'm going to say find the consensus terms in the following expression. And that expression will be this: A naught and C naught and D, or A naught and B and D, or B and C and D, or A and B and C, or A and C and D not. So we're going to find the consensus terms in this expression. And I'll give you a hint, there are at least 3 of them. I'll do the first one for you, but then I'd like for you to find the other 2. So the first one I'm going to take from the, what are we going to do? The second term and the fourth term, A naught, B, and D, or A, B, C. And here's the trick. You look at the terms and you figure out, well, what is the one variable that's inverted between the 2, right? In this case, it's the A's, right? So this first term has A naught, then B and D, and the second term has A, then B and D. So it has, they share a variable that's been inverted. And that can only happen once. And so those guys produce, you take everything else that's left over in those terms and you add them together. So what we would do is we would take from the first term B and D and AND it with B and C. And then of course anything ANDed with itself is itself over again. So that means the consensus term is B and C and D.
So the second one, could it be A naught, C naught, D, or
Well, you're saying A naught, C naught, and D, or
B, C, D?
B and C and D. Okay, First question, which variable are you using to combine these terms?
C.
C, yeah. C, which means you're going to get, from the first term, A naught and D, right? And from the second term, you get B and D, which means what's our consensus term?
A, B, and D.
Yeah, good. A naught, B, and D.
But like you said, it can only, so what if there's one, what if there's, say for example, could you do A naught and C naught and D, or A naught, or A and B and C? Could you do that?
Wait, say that again?
A naught, C naught, D,
A
or
naught.
A, B, C.
Or A, B, C. Okay, that's worth discussing. What variables do you want to use to combine, or what variable do you want to use to combine these?
So this, it has two, right?
Yeah, so which one do you want?
We could do A as well.
Okay, so let's go off A, which means that we're going to get, for the first term, C naught and D, and B and C. What is that going to equal to?
Just B, it would be B and D, correct?
No. What is the C naught and C going to get us? Right, what's X and X naught? It's 0. You're absolutely right, which means that this is going to be equal to 0. If two terms have more than one variable that's inverted in both of them, then its consensus term will be 0. So they don't have a consensus term. But I'm glad you said that, because that gave us an opportunity to illustrate that. All right, we're going to find one more. Oops, sorry. All right, a couple places we've got. Yeah, say it one more time. BCD or ACD prime. All right, and which variable? No, I'm saying which variable are you using? Yeah. So that's going to get us what? Good. B and C and A and C, which is going to get us A, B, and C. Cool. Okay, so here's the thing. All three of these are consensus terms. And the whole point of finding our consensus terms is so that we can reduce the size of our expression, right? It's all about simplifying. But here's the thing. One of our three appeared to form the other two. So here's the thing. If you eliminate a consensus term, you cannot use that term then to eliminate other consensus terms, right? So in this example, would we want to eliminate BCD as a consensus term? No, right? Because if we did that, then we couldn't eliminate the other two terms, and we'd much rather eliminate two terms instead of eliminating one term. So we're going to eliminate these two terms, but we're not going to eliminate BCD.
Isn't A naught BD also used for the first one?
What's that?
The second consensus term, isn't that also used to form the first consensus term, A naught BD? If you have A naught BD or
dude, you get a gold star, man. I've used this example for the last like 4 semesters. You're the first person that's ever noticed that. Because the example's always set up about BCD, but yeah, he's right. We're actually in trouble in both cases because we can't eliminate this because of that. Well, actually, I take that back. We are okay, and why are we okay? Never mind. It's a silver star now. Why are we still okay? Because we're not trying to eliminate BCD anyway. We're trying to eliminate A, not B, and D, and ABC. Right? We're keeping BCD. This is why we want to keep BCD. Okay. You freaked me out there for a second. I was like, oh my gosh, this example broken. I've been using it forever. All right. So yeah. So let's go ahead and make a little note there that just says, if a consensus term is removed, or any term really, it cannot be used to form other consensus terms. All right. Any questions about that? That's the consensus theorem. Okay. Moving right along. So the last thing we want to talk about today, to wrap up our discussion of Boolean algebra, part 3 here, we're going to call this Techniques for Algebraic Simplification. Techniques for algebraic simplification. All right, and what we mean by that is we have all these theorems, right? We have all these tools that we can use, but you can look into the expression and be kind of confused about where to start, right? Well, what do I use first, and what order do I do things in? Is there a sort of an algorithm that I can use to sort of streamline these things? And it turns out the answer is yes, and that's what we're going to talk about. So the order in which we will try to apply things when doing simplifications or doing optimizations with Boolean algebra is this. Step 1, we will use the uniting theorem to combine terms. Start by using the uniting theorem. Take a look at the expression, try to rule out any possible place you can use to apply the uniting theorem, because the uniting theorem gives you the most bang for your buck. Right? You will reduce the most stuff with the uniting theorem. And once you've exhausted all of the opportunities to use the uniting theorem, the next step is to eliminate redundant terms with the absorption theorem. So eliminate redundant terms with the absorption theorem. Step 3, once you've done that, is eliminate redundant literals. Redundant literals using the elimination theorem. then finally, step 4, and this is kind of as a last resort. If it's just, you've done everything else and it's just not quite as optimized as you think it can be, or as, more importantly, as the test question says it needs to be, as a last resort, use the consensus theorem to add terms. Okay, 2 things I want to hit right now, because we haven't really talked about it. I've used these words a couple of times. First off, everyone good on the procedure here? The list? Everyone got the list jotted down before I move off of it? Okay. I think I've used these words, but I haven't really stopped to explain what I'm talking about. And what I mean by that is, in fact, let's call this 3A. Variables versus terms versus literals. What I mean by that is, let's look at an expression. If I have f is a function of a, b, and c is equal to a, b, c, or a naught b, or c, or a, c naught. Okay? The first question here would be, how many variables? And the answer to that question is 3. When we say variables, it's how many unique variables appear or are used in this function. So this function is a function of a, b, and c, so it is a function of 3 variables. The next question, right, is how many terms. Now, when we say terms, we refer to terms in the sense of when we talk about product of sums or sum of products, right? The groups of things, the groups of variables, right? In this case, there are, let me use a different color, 1, 2, 3, there are 4 terms, right? A term, a term, a term, a term. Does that kind of make sense? Even a term that contains only 1 variable is itself still a term. And the last question is, how many literals? And a literal is a instance of a variable within a term. So there are, let's see, let me speak. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 literals in this expression. Does that make sense? So a variable is how many unique variables appear in the expression. In this case, 3. A term is how many groups of literals are there in the expression. That can change depending on how you've optimized. And a literal is an instant, a unique instance of a variable in a term. So in this case, there are 8. You just count all the variables in the function. That's how many literals there are. Okay? Does that make sense? Any questions about that? Okay. So that's when we say, if I go back up here to our list of things to do, right? Use the uniting theorem in step 1 to combine terms, right? We want to take terms, but this lets us eliminate terms altogether, eliminate redundant terms, so entire terms with the absorption theorem. But here in step 3, it says eliminate redundant literals using the elimination theorem. So we're only going to reduce and eliminate single literals. So you can see how, again, there's sort of more bang for your buck depending on which one you use. Now, why would we want to use, in step 4, the consensus theorem to add terms to our function? When the whole goal is to reduce the number of terms and literals in our function, why would we want to add some as a part of our simplification process?
You could reduce the amount of literals.
What's that?
You could reduce the amount of literals.
It's not that you can reduce the amount of literals, because we're still going to be adding stuff to the expression.
Or, I mean, terms, actually.
They will help us reduce the number of terms. In our consensus term thing here, right? We talked about how BCD could be used to create consensus terms from the other two guys, right? So BCD was a player in the creation of these two other consensus terms. What if BCD wasn't present in the expression to begin with? We could add BCD to the expression, right? Using A not BD or ABC, and then use it to eliminate two terms, right? So that lets us, we're essentially going to add one to set up eliminating two, right? So we lost one. Does that kind of make sense? This last step is fishy, which is why I say use it sparingly, only use it as a last resort, but it is a thing that you can do. So with our last few minutes here, let's go ahead and work an example of using all of those steps. So I'm going to say, as example, use all 4 steps to simplify the expression and it's a monster. A naught, B naught, C naught, D naught, or A naught, B, C naught, D naught, or A naught, B, D, or A naught, B, C naught, D, or A, B, C, D, or A, C, D naught, or B naught, C, D naught. Okay, so I'm gonna do some things. I'm gonna grab this so I can copy and paste it. Copy. Okay. Whoa, what are you doing, man? Okay, freaking out. Step 1. Use the Uniting Theorem. All right, x, y, or x and y naught is equal to x. There we go. Okay. So in this expression, since we're kind of running out of time, I'm going to go ahead and just work through it instead of doing the rhetorical thing where I ask you guys to take a look at it and tell me what you see. We can use the Uniting Theorem on these first 2 terms here. We can say let x equal a prime, c prime, and d prime, right, because it appears in both, and let y equal b. So that will reduce to just a prime, c prime, d prime, and the rest of the expression. A naught b d, or a naught b c naught d, or a b c d, or a c d naught, or b naught c d naught. Right? So I was able to use that expression and reduce it all down. So let me copy that. It's like my tablet gets sleepy towards the end of class and it starts slowing down. Okay. So step 2, use the absorption theorem. that says that x or xy is equal to x. Now I can use that in these second terms, a naught b d or a naught b c naught d. Let x equal a naught b d, and let y equal c naught. So from there we can eliminate that third term and have a naught c naught d naught, or just a naught b d, or a b c d, or a c d naught, or b naught c d naught. All right, move along. Step 3, use the elimination theorem. Says x or x naught y is equal to x or y. Now if I set up our expression, and I know this is kind of dry, so I appreciate you guys bearing with me. BD or ABCD or AC naught. Sometimes you have to do an intermediate step in order to use elimination. You have to factor some stuff out. So for example, in these first two terms, I'm going to factor out BD. I'm going to say BD and A naught or AC. Does that make sense? So here is my place to use the elimination theorem. So I'm going to have BD and A naught or C. And then I'll factor everything back in and get A naught, C naught, D naught, or A naught, A naught BD, or BCD, or the rest of it, A, C, D naught, or A, C, D naught, or B naught, C, D naught. And finally, the last step here was use the consensus theorem. All right. So we'll start with our expression. A naught, C naught, D naught, or A naught BD, or BCD, or AC, D naught, or B naught, C, D naught. And what I'm going to do is I'm going to find a consensus term from BCD and ACD, BCD or AC, D naught. I can take my consensus term off of the D's, and that's going to leave us with a BC. So, godlings, the last time I have to write this expression, A naught, C naught, D naught, or A naught, BD, or BCD, or AC, D naught, or B naught, C, D naught, or finally, now we have ABC hanging off on the end. Here's the kicker. Oftentimes, not always, but oftentimes, you can use the consensus term to essentially have the consensus term murder its parents, and turn around and eliminate the terms that were used to create that consensus term. So for example, on ABC, I can take what? The B and the B naught from B naught, C, D naught. I'll call that 1. And I can also eliminate from A naught, B, and D. We'll call that 2, just to label them.
Could you use this, so you're saying you can use the same expression twice?
What's that?
You can use ABC twice?
To create consensus terms? You bet, yeah. That's the sort of superpower of it. So that first term, A, B, C, or B naught, C, D is going to yield what? A, C, and C and D naught, which is A, C, D naught. The second one, we have A naught, B, D, or A, B, C. That yields B, D, and B, C, which is going to give us B, C, D. And we see that A, C, D naught appears there, and B, C, D appears there. Again, like I said, these were the two terms that were used to create our new consensus term, which is the sort of thing that doesn't always work out that way, but it works out enough that it's sort of worth talking about. And so after all of that, we can eliminate those two terms, and we can say our simplified result is A naught, C naught, D naught, or A naught, B, D, or B naught, C, D naught, or A, B, and C. And there we go. There's our final result. Okay, I know that was long and pretty boring and kind of dry, but hopefully that illustrated how we can sort of step through the process of knocking them out. Boolean algebra simplifications take a long time. They're long, they're dry, they're boring, but you know, you gotta do them. So, any questions, comments, or concerns?
This will be uploaded?
It already is, man. It's up there now. Yeah, happened in real time. Okay, if not, so that's the end of chapter 3. So the due date for the Unit 3 assignment we push back to the Wednesday, next Wednesday, a week from today.
Yeah.
And we will pick up in chapter 4 on Friday. So, thank you. Stay safe, stay warm. I'll see you later.